In mathematical logic, a well-formed formula, shortly WFF, often simply formula, is a word that is part of a formal language. A formal language can be considered to be identical to the set containing all and only its formulas. A formula is a syntactic formal object that can be given a semantic meaning by means of semantics. Introduction. A key use of formulae is in propositional logic and predicate logic such as first-order logic. In those contexts, a formula is a string of symbols phi for which it makes sense to ask, is phi true? Once any free variables in phi have been instantiated. Although the term formula may be used for written marks, it is more precisely understood as the sequence being expressed, with the marks being a token instance of formula. It is not necessary for the existence of a formula that there be any actual tokens of it. A formal language may thus have an infinite number of formulas regardless whether each formula has a token instance. Moreover, a single formula may have more than one token instance, if it is written more than once. Formulas are quite often interpreted as propositions. However, formulas are syntactic entities, and as such must be specified in a formal language without regard to any interpretation of them. An interpreted formula may be the name of something, an adjective, an adverb, a preposition, a phrase, a clause, an imperative sentence, a string of sentences, a string of names, etc. A formula may even turn out to be nonsense, if the symbols of the language are specified so that it does. Furthermore, a formula need not be given any interpretation. Propositional calculus. The formulas of propositional calculus, also called propositional formulas, are expressions such as: their definition begins with the arbitrary choice of a set V of propositional variables. The alphabet consists of the letters in V along with the symbols for the propositional connectives and parentheses, all of which are assumed to not be in V. The formulas will be certain expressions over this alphabet. The formulas are inductively defined as follows. Each propositional variable is, on its own, a formula. If phi is a formula, then phi is a formula. If phi and psi are formulas, and is any binary connective, then is a formula. Here could be the usual operators, or, this definition can also be written as a formal grammar in Bacchus NAUR form, provided the set of variables is finite. Less than alpha set greater than, equals P, Q, R, S, T, U. Less than form greater than, equals less than alpha set greater than, less than form greater than. Using this grammar, the sequence of symbols is a formula, because it is grammatically correct. The sequence of symbols, P, is not a formula, because it does not conform to the grammar. A complex formula may be difficult to read, owing to, for example, the proliferation of parentheses. To alleviate this last phenomenon, precedence rules are assumed among the operators, making some operators more binding than others. For example, assuming the precedence 1, 2, 3, 4. If the precedence was assumed, for example, to be left-right associative, in following order, 1, 2, 3, 4, then the same formula above would be rewritten as predicate logic. The definition of a formula in first-order logic is relative to the signature of the theory at hand. This signature specifies the constant symbols, relation symbols, and function symbols of the theory at hand, along with the arities of the function and relation symbols. The definition of a formula comes in several parts. First, the set of terms is defined recursively. Terms, informally, are expressions that represent objects from the domain of discourse. Any variable is a term. Any constant symbol from the signature is a term. An expression of the form f, where f is an NARY function symbol, and T1, Tennessee terms, is again a term. The next step is to define the atomic formulas. If T1 and T2 are terms, then T1 equals T2 is an atomic formula. If R is an NARY relation symbol, and T1, Tennessee are terms, then R is an atomic formula. Finally, the set of formulas is defined to be the smallest set containing the set of atomic formulas such that the following holds. is a formula when is a formula, and a formulas when and a formulas, is a formula when is a variable and is a formula, is a formula when is a variable and is a formula. If a formula has no occurrences of or for any variable, then it is called quantifier-free. An existential formula is a formula starting with a sequence of existential quantification followed by a quantifier-free formula. Atomic and open formulas. An atomic formula is a formula that contains no logical connectives nor quantifiers, or equivalently a formula that has no strict subformulas. The precise form of atomic formulas depends on the formal system under consideration. For propositional logic, for example, the atomic formulas are the propositional variables. For predicate logic, the atoms are predicate symbols together with their arguments, each argument being a term. According to some terminology, an open formula is formed by combining atomic formulas using only logical connectives, to the exclusion of quantifiers. This has not to be confused with a formula which is not closed. Closed formulas. A closed formula, also ground formula or sentence, is a formula in which there are no free occurrences of any variable. If A is a formula of a first-order language in which the variables v1, vn have free occurrences, then A preceded by v1, vn is a closure of A. Properties applicable to formulas. A formula A in a language is valid if it is true for every interpretation of. A formula A in a language is satisfiable if it is true for some interpretation of. A formula A of the language of arithmetic is decidable if it represents a decidable set, i.e., if there is an effective method which, given a substitution of the free variables of A, says that either the resulting instance of A is provable or its negation is. Usage of the terminology. In earlier works on mathematical logic, formulas referred to any strings of symbols, and among these strings, well-formed formulas were the strings that followed the formation rules of formulas. Several authors simply say formula. Modern usages tend to retain of the notion of formula only the algebraic concept and to leave the question of well-formedness, i.e., of the concrete string representation of formulas, as a mere notational problem. However, the expression well-formed formulas can still be found in various works. These authors using the name well-formed formula without necessarily opposing it to the old sense of formula as arbitrary string of symbols, so that it is no longer common in mathematical logic to refer to arbitrary strings of symbols in the old sense of formulas. The expression, well-formed formulas, also pervaded in popular culture. Indeed, WFF is part of an esoteric pun used in the name of the academic game, WFF, N-proof. The Game of Modern Logic, by Layman Allen, developed while he was at Yale Law School. The suite of games is designed to teach the principles of symbolic logic to children. Its name is an echo of whiff and poof, a nonsense word used as a cheer at Yale University made popular in the Whiff and Poof song and the Whiff and Poofs.